Okay, in this podcast we're going to take a look at the introduction to energy. This is a unit on thermochemistry. The ability to do work or transfer heat. This work is the energy used to cause an object that has mass to move. So we can think about swinging a tennis racket and hitting the ball. So we use energy to do that work. This ball or the racket is going to move some distance with some force, and that's what work is. Now, usually when we are talking about work for chemistry, we are talking about gases. Work is used a lot when you're in physics. So if you're in physics, you probably have heard about work already. But in chemistry, generally, we are more interested in heat, but when we are looking at work, it's usually because we have a gas that has been developed in a chemical reaction, and we are looking at what happens to that gas. Are we creating more gas? And if we are, then that gas can create work. It can push against this piston and cause it to rise. And if that were happening, the gas would be causing work on its surroundings. Okay? Or if we have a reaction that causes less gas, we have less moles of gas when we're done, then there'd be work done on the gas by the surroundings because the piston would lower. Okay. More commonly, though, we are talking about heat in chemistry. So it's the energy. Heat is the energy used to cause the temperature of an object to rise. Okay? So if I imagine I have a hot object and a cold object, and I put them together, that heat is going to be transferred from the hot object to the cold object. It always goes from hot to cold. It never goes from cold to hot. So this is what we call heat. The temperature changes, goes down here and goes up here until they are at the same temperature. So let's think about whether we have an endothermic or an exothermic reaction going on, or process going on, because this is not a chemical reaction. This block A, what do you think? Is it going to have an endothermic or exothermic process going on when it gets together with the cold block? Well, if you said it was going to be, this is exothermic because the heat is leaving this block, and it's going to be endothermic because this heat is entering this block. Okay? Alright. Sometimes you can have things that happen that have both heat and work going on at the same time. So if you think about a battery, if it's running, let's say, a fan, a little portable fan, it certainly generates heat. You know, if you touch a battery when it's operating, it gets warm. But it also, in this case, is causing work to be done, or the rotors of the fan to spin. Okay? If I took that same battery and just created a closed circuit, right? Just created this closed circuit, then that battery is just generating heat and no work, and it will run out pretty quickly. Alright, so when we're talking about heat, let's talk about calorie, because that's a term that we often use and you're probably familiar with. So a calorie is actually defined, even though it's something you usually think about in relative to food. Calorie is a unit of heat, and it's the unit of heat required to raise the temperature of 1 gram of water by 1 degree C. So let's think about that. How much energy or how much heat would it take to raise the temperature of the water in this 1 liter bottle from 22 C to 70 C? So 22 C, that's about room temperature, 70 degrees F. And let's imagine I leave a bottle in my car. It's probably going to be about 90 degrees F before too long if it's over the summer. Okay, so let's think about how much heat that's going to take. And go ahead and see if you can figure it out. And pause and then provide your answer. So the calorie you're used to hearing about is, if I look at what are the calories associated with a large popcorn at the Regal, and it might say it's 900 calories, let's say, but that's really not a calorie, that's a kilocalorie. Okay, so when we use a small c, that means calorie. When we are talking on the stuff on food labels, it's a big C, which really means the same thing as a kilocalorie. So maybe even a little more depressing is that popcorn is 900 calories, but it's 900 kilocalories or 900,000 calories. Okay, the other thing we can think about is energy in terms of potential energy and kinetic energy. So potential energy is the energy of an object possesses by virtue of its position. So this biker has potential energy stopped at the top of this hill based on the height off the ground, or based on its relative position, okay? This distance. Okay. As opposed to kinetic energy, which is the energy, same definition, but we change one word. Kinetic energy is the energy of an object possesses by virtue of its motion. So as that biker goes from the top of the hill, goes down the hill, that potential energy gets converted to kinetic energy. So kinetic energy is often called the energy of motion. So let's take a look at a simulation that we have. So here we have a skate park, and I could put a skater on there and have them skate, or I could make it a bug and have them skate. But it's a little easier for me to think about this in terms of just an object. So I'm going to use a ball, and I want that ball to have a little bit more mass. So I'm going to change it from 5 kilograms. Let's say I make it 50 kilograms. It doesn't really matter where you start. So I can start this ball anywhere on the track that I want to. And what I want to do is I want to look at what's happening with the energy of the ball relative to its potential energy. So I'm going to move this over here so we can watch it. And I'm going to start with the ball, let's say right here. And so let's say, take a look what's happening. Alright, let's do that again. As that ball came down, as it came down the hill, its potential energy in joules on the x-axis, it went down. Let's see it again. So as the ball goes down, the potential energy is going down with it. Okay. So let's see what's happening at the same time with kinetic energy. Kind of an interesting picture, right? As the potential energy goes down, as the ball goes down the hill, it's being converted to kinetic energy, or the energy of movement. Okay. Let's take a look at what's happening with the total energy. So as I move down that ramp, okay, so potential energy, kinetic energy, they're exactly inverse of each other, right? And then the total remains the same, which brings us to the law of conservation of energy. Energy is always constant within a system, within an isolated system, right? The energy in that system, assuming the energy can't leave or come in, is always going to be the same. And it's just a difference of whether or not it's potential or kinetic, or where on the scale of them both are. Okay, so let's take a look over here. So let's see, what do you think is going to happen? I'm going to start the ball right here. Do you think that the ball is going to make it over the hump? All right, make a prediction. All right, so let's see what's going to happen. All right, it did make it over the hump and actually jumped right over, right? Let's see if we move this up a little bit. It's going to happen here. Is it going to make it over? Make a prediction. Let's see. It does not make it over. So why does it not make it over? It's because it does not have enough energy to get up here. The energy started here, let's say here, and I need it to get up a little bit higher, and whatever energy it starts with, whatever potential energy it starts with is the maximum amount of total energy I have, and I can't convert something to kinetic energy that isn't there. So because I'm not starting high enough. Now if I start the ramp up here, now of course it makes it over the hump. Okay, let's go back to our slides. The formula for kinetic energy is 1/2 mv squared. Okay, and if we look at it, is 1/2 mv squared. So what is m? M is the mass, right? So the mass is going to be in SI units, and the SI units for mass are kilograms. And what about V? What is V? V is velocity, and back, velocity is really what we think about as speed, kind of. It's some distance over time. So we think about things like miles per hour, right? It's some distance over some time, okay? And the standard units for distance, the SI units, are meters, and the standard unit for time is second, okay? So the standard units here will be kilograms over times meter squared over second squared, right? Because this whole thing has to get squared. Okay? Okay. So we talked when we were looking at that chart, at the animation there, that the first law of thermodynamics. That first law of thermodynamics is nothing more than the law of conservation of energy, and the law of conservation of energy says the same thing as the law of conservation of anything says, that thing cannot be created or destroyed, right? So the total energy of an isolated system. So energy can't be transformed, but energy can be transformed. We just saw it go from potential to kinetic, but it can't be created or destroyed. Okay. All right, so we just said that the units of energy, when we calculated kinetic energy, it was 1/2 mv squared, and we said the mass is in kilograms, because that's the SI unit for mass. Meters per second is the distance over time units, right? And as it turns out, this definition, 1 kilogram meter squared over second squared, is the definition of a joule. So this, my friends, is the SI unit for energy, and it's the one that we will use. Okay, you will often see in the United States, we still talk about calories, and we are the only ones. Most other countries will talk about joules, and you can even see on this Diet Coke can over here that this is a low joule cola. We would call it a low calorie cola. Okay. All right, so here's one last problem I want you to try to solve. Try to solve it, enter your answer.